That's not the order they were turned in. All right, so I'll start to talk about what have we done conceptually to change from the '08 models to the '13 models. And so here are the main features that we dealt with. We changed the way we did nonlinear site response. So we changed from using peak acceleration to using the spectral acceleration on rock at the period of interest. This doesn't change the model very much in the end, but it makes it a little easier in the implementation for hazard calculation. We limited so before we had a style of faulting and depth Z-Tor scale factors. In this model, we limited their impacts to earthquakes over magnitude 4.5 and really tapered it from 5.5 down to 4.5. And the reason was we got a large difference in these effects when we went down smaller. And I didn't want the smaller earthquakes to sacrifice the ability of the model to work in the larger magnitude range. So for both of these effects, I think we work better above magnitude 5.5, and it gets progressively worse as you go down to magnitude 3s. In general, we had a weaker style of faulting factor for the small magnitudes, and we had a stronger depth scaling for the small magnitudes. We did use the finite fault simulations to constrain the magnitude dip and distance dependence for hanging wall effect. So previously, we had a hanging wall factor in there, but it was very poorly constrained on how it scaled for different scenarios. So now we have a better constraint on that. And we had to, like I think everyone else, added another break in the magnitude scaling below magnitude 5.5. You have to do that to fix the overprediction we had previously at these small magnitudes. And it's just a necessary based on the basic scaling of earthquakes. So then the question is uncertainty in the normal style of faulting factor. So I'll show two plots for this. One is these are so for our model, the A12 shown by the red dots here, red symbols, are our normal style of faulting factor. So 0 would be no factor. These are in natural log units, Ralph, not log 10s. So a 0.7 is a factor of 2. 0.2 is about 25%. So the points there, this is a function of period, just the statistical uncertainty in the estimate of the coefficient. And you can say how that changes with period. So the error bars are the standard error, the coefficient. The red line is what we used in our model, so we just used the constant of a 10% reduction. But you can see here at the shorter periods, this is probably uncertain to plus or minus 0.1 or so magnitude units. Here I would say if you really wanted to capture the whole range, put in plus or minus 0.15. At long periods, you can see what happens to our style of faulting factors. They go very negative. The data are becoming less reliable out there. We have fewer data points to work with as well. But I don't know what to do with that. And so I did not let the model go down, and I forced it to stay at a high value. If you look at how these event terms are in terms of looking at style of faulting factor at 5 hertz and at 1 hertz is shown here. So this is versus rake. So the normal faulting events are here. Each symbol on this plot is 1 earthquake. So you can see we have a lot more reverse and strike slip earthquakes than we have normal earthquakes. These are centered near 0, but this lack of having a lot of recordings is part of what gives us a higher uncertainty in that factor, or a lot of earthquakes. And most of them are blue, which is the non-California earthquakes. So the red is the California ones. Next one was my uncertainty in the hanging wall effect. So this is, again, the statistical uncertainty in our hanging wall coefficient. This is in our model, this is A13, again, natural log units. So it's close to a factor of 2, if 0.7 being a factor of 2 here at short periods. And the standard error of those coefficients is about 0.2. Okay, so it's plus or minus 0.2 that could be moving up and down on the hanging wall effect. And then at longer periods, we have a much smaller hanging wall effect. When we look, so our uncertainty, what I would propose to use here is plus or minus 0.2 natural log units. Then if we also look at the residuals for hanging wall, this is for sites only, excluding anything off the edge of the rupture. So it's just in the, either on the footwall or hanging wall side, but within the rupture dimensions. And so this is on the top are this is all 5 hertz. That's earthquakes greater than 6.5. The bottom is greater than 6.5 and within 2 kilometers. And then as a function of dip, this is a function of magnitude and is a function of the distance as you're moving over the hanging wall side. So we have a lot of recordings right over the rupture, the joiner bore distance there near 0. If you look at the magnitude scaling, you can see that there's a starting to get a bias in our magnitude scaling here. At lower magnitudes, the earthquakes or the ground motions are higher. That's consistent with what we were seeing from the simulation, showing some stronger scaling in the smaller magnitude 5 to 5.5 effects. And so while we had near 0 here, these are going positive, indicating we're under predicting the ground motions from small magnitudes on the hanging wall side. Uncertainty of the magnitude 8 at 5 and at 300 kilometers. So so the way we dealt with magnitude 8s, we forced, so let me start with the 5 kilometers. We forced full saturation in the model. That controls part of the magnitude scaling. The data that we have tend to show oversaturation. And so if you're going to build in uncertainty into the model, it really should be skewed to the lower side if you're going to try to capture the observation that the data are lower than our model. So if we add uncertainty, it should be skewed distribution. And then also, I would be saying, look at the epistemic uncertainties that Linda and Bob have been doing, and they're going to show those as well. So if we look at our event terms for magnitude 8, or big magnitudes, this is again 5 hertz and at 1 second. You can see we have just a few recordings to work with, say between 7.5 and 8. And this is the same set for 1 second. These are all lower than 0. These are on average a little bit lower than 0. So if I was to put uncertainty on the magnitude 8 prediction from my model, I would put the event term could be plus 0.25 or minus 0.5 in terms of the way I would skew that distribution. So coming basically from here to down there is where the center could be, and I would have used just the same value for this other periods or similar ranges. If we also then look at what's happening at short distances, so if you want to bring it back to 5 kilometers, this is the data in the western US, our residuals, our within event residuals, and this is our magnitude 7 bins, so from 7s and larger. These are the average residuals are shown here, but within 5 kilometers, this is now the data that we have to work with. There's about 15 to 20 recordings at less than 5 kilometers. If you're going to use that number of recordings and its standard error, you get an additional variability of about 0.15 natural log units in this range. So if I was going for magnitude 8 at 7.5, I would combine the uncertainty that we have the right distance scaling in close with the uncertainty on the overall event term or magnitude scaling as showed in the previous plot. At 300 kilometers, I wouldn't use this information. I don't think it's relevant. You need to go to the Arizona data and just check with that and see what the models are doing. Because fitting this doesn't give me any confidence that I'm fitting the ground motions in Arizona. So I would use that, but then combine it with the previous number here for the event term uncertainties. What's my uncertainty of the standard deviation? So we're into, those of you on Yucca Mountain, these are our sigmas, if we talked about before. How well do we know the standard deviation? So to do this, I would be using the site-to-site standard deviation that's been computed. So this is the within event, the PSS values for the site-specific uncertainties. Linda's going to be showing an update on this, but Adrian worked on this for the Swiss project in looking at a lot of data from Japan and in other areas. And the standard deviation of that within event term is about 0.08 natural log units, and that's what I would still be using here for that model. This then needs to be combined with the tau uncertainty terms. And that's it for me. That's the one hard reference to find. Okay, so why is our model so much longer at long periods than the other models? We looked at that over and over again, and it depends on which events you're modeling and how you treat them. So we fit Loma Prieta really well at large distances, but we overpredict Elmira Kukapa, and that has lots more data. So if you're looking at individual data points, then we're staying higher than the other models. So 1 second we're staying higher. I don't think that's important here because I would throw all this out and just use the Arizona data to do the check. Because if you're going to adjust the Q model, you have to adjust it with Arizona ground motions or Qs. What's the influence of aftershocks on phi and tau? So I went back and I reran it, taking all of those out, and our standard deviations change only about 0.02 in terms of the values. So it's really small. It's not driving the number up and down in terms of what we're getting for these two sets of standard deviations. Okay? Ralph.
Ralph Archuleta, UCSB. So if you have this break in scaling between magnitude 5.5 and those larger, and the parameter that you have in there basically that we would say coming from the models that were useful in the ground motion prediction equations, these synthetics would only be by the stress parameter. So you're implying basically that the stress parameter is different for smaller earthquakes than larger.
No, and if Anne-Marie was here, she could answer this for you in a great way. So she has done work with Tom Hanks going through that. The break in the scaling as we go below magnitude 5 in particular is driven by kappa. So kappa is cutting out the band limit. So as the corner frequency moves up and kappa is here, you're running out of energy in your spectrum. Your spectrum's getting too narrow. So that's what drives it back down. It's not because the stress drop's slow. So they run a constant stress drop model and can match the data all from magnitude 2.5 all the way up.
Thank you.
Yusef.
Quick question, because yesterday you asked and last night I had more residual evidence.
We can't hear you yet.
Hello?
I think it's on now, Yusef.
Hello?
Right? Yeah.
Yeah. So Norm, yesterday late in the afternoon, you asked what about magnitude 5.5 and less? How does it work in terms of hanging wall, footwall?
So
maybe later if you show residual.
This is our residuals off for the hanging wall. Oh, we only did it for the large events.
Yes,
right.
That's why you asked.
The one place that we had, no, I should take it back. So this one has all of the events, but only with anything with RJBs less than 2. Okay? So these are different sets. Big events only, this is big events less than 2 just for the dip scaling, but this has what you're after, and we have a slope here, so we're under predicting that part of it. So our magnitude scaling in our hanging wall effect is going down pretty fast, and we shut it off at magnitude 5.5. So it's tapered from 6.5 down, and that taper is probably too steep, is really what that's showing. And I didn't want to have a big hanging wall effect at small magnitudes because I was thinking it's a geometrical effect, but the simulations are showing it, and perhaps it's radiation pattern driven or some other effect. But this is consistent with what the simulations that were shown yesterday have. Paul.
Paul Somerville from URS. Norm, I think you said that there is more depth to top of rupture dependence for the smaller events.
Yes.
How do you interpret that?
I don't. It's stronger. We already have a pretty strong scaling with depth to top of rupture. So a factor of 2 over 10 kilometers. And that goes up even more for the smaller earthquakes. So now, is that really stress drop driven? Is it something else? I don't know what the cause is, and we haven't got an explanation for it.
But I guess the smaller the magnitude, the more accurate the point source representation of depth. You know, if you think of it that way, you get a more pure representation of a single depth or depth range.
And you could, and we use top of rupture on all of these. So even on by that point, they are essentially, those small magnitudes, they are points. But you see that. So if I'm going to wave my arms, I could say the smaller magnitudes are sampling, as you said, a little area, whereas the bigger ones are averaging it out over a greater zone. But I don't have any good physical basis really as to why that difference is there. Brian.
Norm, can you comment on that in the middle figure? What those are for small magnitude events, and so the hanging wall being identified as a hanging wall site means there is a finite fault model for small magnitude events. So, do you think is it possible there is a large uncertainty associated with the distance calculation? And
yeah, so there's more. So we don't have the hanging or finite fault models here. All we did was but we do have a joiner bore distance for all of these, and so all of these are joiner bore distances less than 2, but that's all we know for the small magnitudes. So it's essentially saying the epicentral distance is less than 2 kilometers.
right, but it could be that the fault may be not dipping in.
Correct. Could be off. That's right.
Okay.
That's right. So I don't. This is getting less and less reliable.
Right.
But this trend, if I'm going to look at it right now, is I could say not inconsistent, if you want to put it that way, with what's coming out of the simulation, saying there is still something higher, even for those little earthquakes.
Yeah, but it also can be. I mean, is there other way to improve the fit to those data points, other than hanging wall effects?
Probably you could, as you said, maybe the distances are off, and this is part of what, we're back to why are there standard deviations going up at short distances from these smaller magnitudes that Linda will talk about later on.
Okay.
And whether, is that radiation pattern differences that are showing up? Is it errors in the magnitude? Is it errors in the distance or the location of the source such that the nearby distances are off? All of those could contribute, but we don't have a good answer.
Okay.
I don't have a good answer, I should say.
Okay. And another clarification question is, you talk about using the local dip angle and rake angle.
Mm-hmm.
Did you actually use it in your development of the GMP, or are you still using the global average values?
So we took a separate input column from what everyone else had done. So, that is using the dip and the rake of the closest segment.
Okay, so that's what's using your GMP.
Mm-hmm.
So that's different from what you did in 2008.
Correct. 2008, we didn't ever tell you what we did. So I actually changed it. So on Denali, for example, the pump station 10 is close to one segment and it's a different dip. And I went in and changed that on my own model. So that's an undocumented revision. So that part of the model had the local angles in there.
How about depths to top of rupture? Did you do the same for depths?
No, I just used the global number for the depth to top of rupture. Any other questions? All right.